Have you ever noticed how iron rusts in air to form reddish-brown iron, 3, oxide, but in other cases it forms a green iron, 2, compound? What allows a single metal to behave so differently in different settings? That's the magic of variable oxidation states, a signature feature of the d block or transition elements. These elements have electrons in both their outer ns and penultimate n-1 d orbitals. Because the energy difference between these orbitals is quite small, electrons can be lost from both, giving rise to multiple oxidation states. Take iron, for example, it exists as Fe2+ and Fe3+ in different compounds. Manganese goes even further, ranging from +2 all the way to +7. As we move across the 3D series, low oxidation states dominate at the beginning and higher states become more stable toward the center of the block. These versatile oxidation numbers also explain why transition metals make excellent catalysts. For instance, vanadium pentoxide, written as V2O5, plays a vital role in the contact process for making sulfuric acid by flipping between oxidation states to help the reaction proceed. Have you ever admired the deep blue of copper sulfate crystals or the violet hue of chromium salts? These stunning colors come from a phenomenon known as D-transitions. In transition metal ions, the partially filled d orbitals split into different energy levels when surrounded by ligands, a concept explained by crystal field theory. When light hits these ions, electrons jump between the split d orbitals, absorbing certain wavelengths and reflecting others, and that's what gives rise to color. For example, Cu2+ appears blue, Ni2+ is green, and Cr3+ has a beautiful violet tint. But when d orbitals are either completely full, as in Zn2+, or completely empty, as in Sc3+, there's no possibility for d transitions and hence no color. These ions are colorless. On screen, you'll see a diagram showing how d orbitals split in an octahedral field. It's this splitting and subsequent electron transition that lies at the heart of transition metal colors. Now imagine a metal ion surrounded by a swarm of molecules or ions that attach themselves to it. That's a coordination complex. Transition metals are masters at forming these complexes because of their small ionic size and high charge density, which make them attractive to ligands, molecules that can donate lone pairs of electrons. These ligands, such as ammonia, water, chloride, or cyanide, form coordinate bonds with the central metal ion. A classic example is hexacyanoferrite, written as open bracket FeCN6 and tetraminicopper, written as open bracket Q NH34 2+. These complex ions have wide-ranging applications. They give us vibrant dyes, effective catalysts, and even life-saving drugs like cisplatin used in cancer therapy. Transition elements' ability to form complexes is a result of their unique electron configuration and orbital availability, making them chemically versatile and industrially valuable. Have you ever wondered why some substances get pulled toward magnets while others don't? In the world of transition elements, this magnetic behavior arises from unpaired electrons in their d orbitals. The more unpaired electrons, the stronger the magnetism. This is called paramagnetism, a property displayed by most transition metal ions. On the other hand, ions with all paired electrons, like Zn2+, are diamagnetic. They are slightly repelled by a magnetic field. We can calculate magnetic moment using the formula mu equals the square root of open bracket n times n plus 2 close bracket, measured in Bohr magnetons, where n is the number of unpaired electrons. For example, manganese 2+ has 5 unpaired d electrons, giving it a magnetic moment of approximately 5.92 Bohr magnetons. Magnetic behavior not only helps us understand electronic structure, but also has practical uses. It aids in identifying oxidation states and configurations in unknown complexes through magnetic susceptibility measurements. Imagine you're cooking and you need a pressure cooker to speed things up. In chemistry, transition metals serve a similar role by speeding up reactions without being consumed. These elements and their compounds act as catalysts in many important industrial processes. Their ability to adopt variable oxidation states allows them to facilitate the transfer of electrons and form intermediate compounds, which helps lower the activation energy of a reaction. For example, iron is used in the Haber process to manufacture ammonia, vanadium pentoxide, written as V2O5, catalyzes the formation of sulfur trioxide in the contact process, and finely divided nickel helps hydrogenate vegetable oils into solid fats. Transition metals can also provide surfaces where reactants are adsorbed and activated. This is called surface catalysis. As you can see on screen, the metal surface attracts the reactants, breaks their bonds, and makes new products more efficiently. These catalytic properties are why transition metals are essential in chemical industries around the world. Let's dive into the fascinating world of interstitial compounds and alloys. Transition metals can trap small atoms like hydrogen, boron, carbon, or nitrogen in the empty spaces, or interstices, of their crystal lattices, forming what we call interstitial compounds. These are incredibly hard, have high melting points, and retain their electrical conductivity. Examples include titanium carbide, TiC, and iron nitride, Fe4N. Beyond that, transition metals also readily form alloys with other metals. By mixing their atoms with elements like chromium, nickel, or zinc, we get materials with enhanced properties. Think stainless steel, brass, or bronze. These alloys are tougher, more corrosion-resistant, and widely used in construction, aerospace, tools, and even surgical equipment. The reason transition elements form such a wide range of alloys is their similar atomic radii and ability to replace one another in the crystal structure without much distortion. Let's quickly revise the remarkable properties we've uncovered about D-block or transition elements. We began with their ability to show variable oxidation states, which makes them useful in redox reactions and catalysis. Then we saw how DD transitions make their ions beautifully colored, with crystal field theory helping us understand the cause. We explored how these elements form stable coordination complexes by binding with ligands like water and ammonia. We delved into their magnetic behavior, linking it to the number of unpaired d electrons. We looked at their powerful role as catalysts, making everything from ammonia to margarine. And finally, we explored their formation of interstitial compounds and strong functional alloys. Transition elements, with their flexible d orbitals and rich electron chemistry, are truly the multitaskers of the periodic table. I hope this session helped you appreciate how D-block elements shape industries, materials, and everyday chemistry. See you in the next class with more molecular marvels and real-world reactions.